So as we continue down our systems analysis phase, we've been looking at some diagrams. We looked at the data flow diagram, was sort of the big deal last time, and before that we were looking at functional decomposition diagrams, and even before that we were looking at mind maps. This here is another set of diagrams we're going to be looking at that all deal with basically object modeling. How would you model objects in your system? Now, like most things, this is going to be kind of a more purist approach. It's just going to look at objects as if, you know, this is the way it is. I would tell you that when you go actually into your places of work or whatever, you're probably going to be using some bits of this and ignoring some other bits. But it's not bad. This is kind of the last bit of modeling we do, and then after that we just got to make one more decision, and then we move into the design phase. So what we're going to be looking at here is we're going to try and figure out how we can actually use object-oriented analysis to describe the system, and then basically define a bunch of terms and explain the relationships between objects and get the concept of inheritance down, and then also talk about basically drawing relationship diagrams. These diagrams, by the way, I'm not going to probably do anything like, you know, I almost killed myself with a DFD. I think what these would be easily done in PowerPoint. One thing I would say is you might want to look at Visio for some of this stuff, or there are free tools like Star UML and all that can get these things going as well. But again, PowerPoint is fine. In fact, if you actually Googled some of these diagrams and you look at some of the images, you can see a lot of them are actually handwritten as well. Anyway, all these diagrams are part of a set of diagrams, and actually a methodology called UML, so Unified Modeling Languages. And you can kind of see right there that we've got, I've been using the term use cases already, but we got use case diagrams, class diagrams, sequence diagrams, state transition diagrams, and activity diagrams. These are the diagrams that we'll be talking about in this particular set, and they will be the kind of diagrams that you'll be asked to do in your homework. All right, and then and I was just talking about using PowerPoint, which is the worst. Well, it's not the worst, but it is one of the worst case tools out there. There are definitely other tools that you could use that would be able to take your diagram and actually generate code, or take code and reverse engineer the diagram. So this is not necessarily an area I work in a lot, so I don't necessarily have any great examples of those tools, but I know certainly that they exist. All right, so object-oriented methodology, right? Now they say it's popular because it integrates easily with some of the various languages. Some of these languages I think you've had some training in, like Java and Python typically are fairly big on this one. Smalltalk, I'm not sure how much that's actually used. It was, however, one of the first, or at least I think, one of the earliest OO languages out there. So they're making a lot of judgment statements on this slide, and I get it. I mean, they're basically saying programmers like using OO code because it's modular, reusable, and easy to maintain. I'd argue that you could do that also with non-OO code too. You could, you know, make code that's, you know, I've been using code that's modular, reusable, and easy to maintain, and they don't do a lot of OO coding, but whatever. At the end of the day, though, we want to basically try and create a model that represents the system in terms of objects. You are an object. I am an object. Your homework is an object. We would want to basically try and create a set of diagrams that would model how all of these objects relate with each other. And so out of this grew UML, right, which was a method of visualizing, documenting a system. Not necessarily, it doesn't have to all be objects, by the way, but this is why I said earlier that you can be using bits of this in different contexts, especially when it comes to use cases. But what you'll see with the Unified Modeling Language, we're going to basically create objects that will have attributes. They'll have methods. Attributes are basically the things that would describe the object. An attribute for me would be my last name, my ID. That would be attributes. Methods would be things that I do, like for example, I grade, I teach. And then the message is some way that my object communicates with you as objects. And so, for example, sending the grade to you, right? That would be sort of a message. Now, Another term that they throw at us right away without any kind of picture yet is this class. So a class is like a blueprint. It's like a blueprint that would be able to create a bunch of the same objects. So Grant Spencer is a instance of the instructor class, all right? Betty Kruger would be the instance of the instructor class. Steve DePay would be the instance of the instructor class. There'd be one kind of description of what an instructor is with the instructor's attributes, methods, and then out of that structure would stamp an instance of that particular class. All right, so here we finally get a little bit of a diagram that we can kind of play with here. All right, so what we see is what they're trying to model is everything going on in basically driving a car, I guess. Yeah, driving a car. Sure, that's what we're doing, modeling driving a car. So in this case, we've got the driver object and the car object. Now, the driver object is going to have attributes that would include things about the driver. So, you know, it makes sense. You hope that there would be a license. Age is kind of a dumb. I would think a date of birth would be a better one for that. You know, maybe record and all that kind of stuff. That would be basically the driver. And then we got the car, which has, you know, the attributes about a car. Now, we haven't talked so much here about the methods yet, but this is more about a message. So when you're in the car and you want it to go faster, you send a message, and you send that message typically, let's using cruise control, by pushing on the accelerator, right? You put your foot on the accelerator, it sends a message to the car starts to move faster. Another thing you could be doing is you turn on the windshield wiper. You send a message to turn on the windshield wiper, and the car object will then turn on the windshield wiper, and there it goes. So that's sort of a little bit of that. This is closer now to what this would look like in a program. We're looking at a different object now. We're looking at a parent object. And by this, I imagine we're actually looking at a legitimate parent, like, you know, what I am a parent. And so the attributes are things that describe the parent, and then these are things that parents do. We read bedtime stories, and we apparently drive in the carpool. All right. Now that's a parent object, or even a parent class, and that stamps out. Sorry, you know, that was totally bad what I just said. This is basically the class, and this stamps out the object, right? So here's Mary, who's an instance of a parent. Ahmed is an instance of the parent. Anthony is an instance of the parent. And this is a child, right? So again, this is not, don't start thinking in terms of systems here. This is a child, like I have 2 children. So again, we got the names and stuff. Number of siblings would be a dumb attribute because you could derive that, I would think. But anyway, these other ones are fine. And then you got your methods as to all the things that they can do. This is sort of the class, and this stamps out the instances. So James, Amelia, and Misty. So attributes basically describe bits of the object, all right? And then the other thing to think about is objects typically have a state. So what is the current state of the object? In the case of the car, for example, you can imagine the state might be its speed, right? Or even the fact that it's on, right? You turn ignition, turn the car on, now its state is on. You turn it off, it's off. You're going at a certain speed, that would be a state, right? So that's what you kind of get. I guess a state would be kind of like an attribute. That's why it's sort of here. Excuse me. Then you have the methods. And you got to imagine these methods are basically just algorithms or realistically programs, right? So here they've got a method called more fries, which I guess could be probably part of a parent method, maybe, if he wants to make more fries. Anyway, and what's the algorithm to make more fries? Well, apparently you heat the oil, you fill the fry basket, you lower it in, you check the things. When you're ready, you drain, you pour it to a warming tray, and because of our diet in this culture, we add salt. All right, so that's like an algorithm, and that's how this particular object makes fries. So that's a method. In Python and in Java, for sure, this is pretty obvious when you define an object. You create an object, you got the attributes, which are basically like the fields that describe that particular instance, and then you get the programs, and those programs are called methods. And then you get this concept of the message. And an object basically tells another object to do something. So it's a command that tells an object to perform a certain action. Now, so there are three ideas that are very important in object-oriented analysis, or OOA. One is encapsulation, polymorphism, and inheritance. Okay, I'm not sure, to be honest, how much encapsulation is dealt with here, but I'm not going to care about that as much as polymorphism is a pretty big deal. Poly means many, morph means shape, so many shapes. Here's the deal: the message "good night." You send a message "good night" to a child, it's going to act differently than if you send the message "good night" to the dog, if you send the message "good night" to the parent. It's the same message, but different, so many shapes, many different responses. I think one of the best examples that's a very easy one for us is print. Most programs have some way to print to the screen. And I don't know if you've noticed, but boy, most times the print method or program is very, very, very flexible, right? You can send in a literal, you can send in, a string literal, a numerical literal, you can send in a date, and maybe that will get automatically translated to a literal. You can send in one of these things, two of these things, you can send in a whole bunch of these things separated by commas in some languages. So print is a very, very flexible thing. I'm just saying print. What my message is to print to the screen. What I put into it, it changes its shape. It does different things depending on what I put into the print. But at the end of the day, I'm just printing to the screen, right? The idea is simple. The execution of the idea changes depending on its context, right? So polymorphism basically says that a message can give different meanings to different objects. So the message, a message to the object triggers changes within the object without saying how, right? So in this case, the instructor, I'm just sending the message enter grade, and I don't necessarily say how. The how is encapsulated inside of this particular object, right? So the instructor just sends a message enter grade, probably shoots a grade in there in with it, and then the instructor has no idea how to enter the grade. It is this object that knows how to do it. It is encapsulated inside of this object, right? So polymorphism, many shapes. Encapsulation basically means that all we need to know is how to talk to this object. We don't need to know how this object does what it does. So a class is an object that belongs, an object that belongs to a group or category is called a class. So all objects within a class share the common attributes. So I think, they got the picture? Yeah, they got a picture here. So let's just talk about the picture. So we have a class called vehicle. So every object or object or instance of vehicle will have a make, model, year, weight, and color, and will be able to start, stop, and park. And that's almost true now. We're about a few years out of having self-driving cars. So there you go. Every vehicle can do that. But, and here's the key to this, we could create a subclass that can do everything a vehicle can do and other things. Okay, so in the case of a car, apparently a car has a make, model, year, weight, and color, and it can start, stop, and park, right? That's it. Minivan, same thing. But now a truck inherits everything there is in the vehicle, and it adds the idea of a load limit. And honestly, as far as methods go, a little bit of imagination, maybe we could also have a sort of a load and unload, which is going to be at least different than it would be for a car, maybe. I don't know. Maybe not. Maybe we should just stuck with the attribute. But load limit here is definitely something that is not typically in a car. And then a school bus has got an emergency exit location. So it inherits everything in the vehicle class, but it also happens to have an emergency exit. So what I'm trying to say is that the school bus class is everything in the vehicle class and something. So when we look at this example, and let's just keep our eyes right in the middle, we have an employee. Now, an employee is a type of person, and that's the way you'd actually say that. An employee is a type of person. An instructor, in the case of our college, is a type of employee. So here's the deal. The person attribute, the person class has got a name, a birth date, and apparently can breathe, eat, and sleep most of the time. So I was having trouble sleeping last night, but the point is they can breathe, eat, and sleep. An employee can also have a name and a birthday, can also breathe, eat, and sleep, but the employee also has a social security number, a telephone number, hire date, title, and pay rate. An employee can be hired, can be terminated, and can change their phone numbers. This is all the things an employee can do, and they inherit all the things a person is. The employee would be a subclass of person. Person would be a superclass of employee. And then over here we've got the instructor. So the instructor can do everything an employee, it has everything an employee has, which is everything a person has. So an instructor certainly has a name because it inherits it through the employee to the person. The instructor certainly has a pay rate because it inherits it from the employee. The instructor can do everything an employee can do, and apparently can teach a fitness class. You don't want to have one of my fitness classes, but apparently an instructor in this model can teach a fitness class. All right? The instructor is a subclass of employee. Employee is the superclass of instructor. All right, so that was a lot about inheritance and then the relationship between them. And one of the things I was trying to say here is an instructor's relationship with employees. An instructor is a type of employee. An employee is a type of object. That's its relationship. All right, and so here we've got this concept again of inheritance. And also, by the way, okay, they're talking about inheritance here. The other idea, which I can't remember if that's actually in here or not. Is it in here? Maybe it's not. Anyway, the other idea is the idea of overriding. So an employee might have a way of getting hired. An instructor might have a different way of getting hired. So what we do is we could have our own little thing here called get hired, and our own version of that method would take priority over the parent method. And so, for example, when it comes to getting hired, I know for a fact that to be hired in any of these colleges I teach at, they have to check into my educational credentials a lot more thoroughly, right? So it's different than if I was to be hired, for example, in a clerical role here. Yeah, my education would be important, but when it comes to actually teaching some of these classes, believe it or not, we're actually pretty vetted. So so there's a slightly different process to getting hired as an instructor than there would be as an employee. All right, so when you got a bunch of different diagrams together, you'll see, here's what I was trying to say, an office staff is a employee, manager is an employee, instructor is an employee. Now that's straight inheritance, okay, that's what that is. But there's other messages too. An instructor can teach a fitness class. A student can take a fitness class. These are all these are people, right? The employee, manager, office staff, instructor, and the student. But then you also have things like the class, the record, and even the schedule. So what I want you to sort of see in this sort of picture, because we're about to leave object-oriented pictures for a bit, is that this is sort of showing all the objects in our system and how they relate to each other. Are they just basically talking to each other, like manager is talking to fitness, or are they inheriting things from each other, like manager is an employee? And I'm not a huge fan of this particular way this diagram is presented, but you'll see if you just Google searches on object relationship diagrams, you'll see they're actually pretty cool. All right. So to sort of standardize this, UML basically came out with a set of symbols. that represent basically a bunch of stuff within systems. And one of them, one set of stuff is all about use case modeling. So use cases are basically some particular thing that happens in the business process. For example, a use case in your example would be student submits homework. That would be a use case. And they would all get around and figure out, well, who's involved with the submitting of the homework? How is that thing actually initiated? And then what's actually involved. So if we look at this, it looks kind of basic. And yeah, I don't think we're going to get to see a full one here, but what we're trying to do in this example is we're trying to basically work out what is the use case, in this case, make appointment, and who is, or what I should say, are the actors. You can almost think of this, if you go back to your DFD idea, of this being an entity and this being the process. I mean, DFDs are older than this, so this set of diagrams kind of evolved from that. And inside make appointment, there'd be a description and a step-by-step of tasks that would be involved to make an appointment. So that's sort of one example. And then here they've expanded it a little bit by basically saying that here the student has got to go and add a fitness class. So the student is the actor. The thing, the use case that they're doing is adding a fitness class, and just so happens that this use case uses that use case. This use case uses that use case. So they're sort of showing you on the one hand, back here, this was just looking at how the actor interacts with the use case. Here, this is talking about how a use case interacts with another use case. Again, similar, I'll probably get in trouble for saying it, but it's similar to the DFD processes when they talk to each other. Now, ovals and stickmen are okay, but typically you do need to start describing some of this stuff. And so here they're basically showing you how to describe a use case. And this is actually pretty formal. I mean, this is the way it's done. Now, I'm saying that there's actually 3 different versions of how to do this. And this is the middle one. There's a very brief one, then there's this one, and there's something called like a fully dressed one, which is more than this. But this is good enough for us for now. And when you get to a shop, what you're going to want to try and figure out from them is what do they do when they're trying to use use cases, because they might not use any of this methodology. But this is not too bad. So the use case here, the bubble is add a new student. Who are the actors involved? The actors involved are a student and a manager. So we're not really seeing that, but I'm going to go back a couple slides for a second. I want you to imagine this guy here would have been, oh geez, what was that? Add new student. That was add new student, right? So this would have been add new student. There'd be a stickman that represents the that actor was what? The student, and another stickman maybe over here that is the manager. Then we got a brief description. Then what is it when it's successfully completed? Now, there's almost always different ways to go through and successfully complete something, right? There's almost always, like, for example, when you're leaving Word, you can go click on File in the menu and click Exit. Another way, an alternative way to exit Word is to click on the X, and then that'll shut it down, right? And notice, by the way, even then there's a couple other things that will happen, right? If you click on File and you click on Exit and you haven't changed the document, it'll shut down. If you click on File and you click on Exit and you have changed the document, a little pop-up come up saying, you know, are you sure you want to leave? That's another alternative, right? And then the same thing when you're clicking on the X. If you change the document, a pop-up could pop up. So even leaving Word has got 4 paths to it, right? So you basically pick what is the most common, what's the desired path, and then the alternative. What has to be true before we even get to this use case, and what is going to be the situation after? And finally, there's a section here for any kind of assumptions, like you know, the student is in a particular faculty, for example, would be an assumption, or the student is a mature student. That would be another assumption. So you get these from this text, you go for the text, and you end up going from the text into this diagram. And this rectangle represents the boundary of the system. Very similar again to the DFD, right? And you can imagine that if this was a DFD, we'd collapse this box and call it auto service department with a 0, right? And then we would blow it up, and this would be like the level 0. So these guys would be like entities, but they're not called entities in this language, they're called actors. And so what we're seeing here is which actors are involved with which use cases. Yeah, I think that's about it for what I want to talk about with use cases. It's certainly about it for what they want to talk about with use cases. The next thing to do is we start talking about class diagrams. So use cases is one set of diagrams. Now we're talking about class diagrams. Class diagrams, for those of you that know what this is, are going to look very similar to ERDs, actually. They feel a lot like them. But remember, classes also have methods in them. So that's one of the differences. But for those of you that know this, they'll still have this concept of cardinality, for example, one-to-manys and stuff like that. And they'll still show how one class, a line will show how one class relates to another class, just like in an ERD, a line typically shows how one table is related to another table. So let's have a look here. Here they're showing the cardinality examples. Notice they're using, that's 1, 0 to many, 1, 0 to 1, 1 to 1, 1 to many, okay? But the actual diagram, this is not a bad example. It's not fully fleshed out in any way, shape, or form. And I would encourage you again to Google search this. But what you can see is you got a sales manager, and by the way, it's not. I'm not saying this diagram is bad. It's just not complete. What you typically would see is someone would have sort of a high-level diagram that you probably talk about in a meeting, but then maybe as you start working on the system, this would be more fleshed out. You'd actually see all the attributes, see all the methods, right? So in this case, this is showing how this object is related to this object. One manager can have 0 to any number of sales reps. One sales rep can have 0 to any number of customers. I suspect if they have 0 customers, by the way, they'll eventually not be a sales rep. Now, one customer will place 0 to any number of orders. An order will have 0 to any number of items ordered. I think that's kind of dumb, by the way. I think an order should have at least 1 item, so I'd be tempted to change that to 1. A sales manager can only manage 1 office. There's a little piece of information there. You can't have a sales manager managing several different offices. And a sales rep, so one office can have 0 to any number of sales rep. A sales rep can only belong to 1 office too. So if you don't know database stuff, I'm sorry. I keep going back to the ERD as an example. But these two diagrams are remarkably similar to each other, and so keep that in mind when you're trying to basically build them. The only thing is that the messages or relationships are spelled out. Like you can't just have one-to-one. You'd actually have to have manages, assigned to. Yeah. All right. So let's leave it at that. So that was a class diagram. Now we're going to go to a sequence diagram. A sequence diagram actually shows the interaction among the classes through time. All right, and how the messages are being passed back and forth. So let me, you can pause and read that, or just read that in your book. But let me show you this. So here is one class. Is this all we're going to get? By the way, we're going to get a better one. We're going to get a better one. Let's get a better one. There it is. All right. We've got 4 classes: student, manager, fitness, and registration record. And what we want to do in this diagram, we already kind of know from the class diagram how they're related, but we don't really know how they work together. And that's what this diagram shows. It shows basically who's the first one to do something, who's the last one to do something. You can tell right now the first one to do something is student, the last one to do something is where the X is. It doesn't necessarily, by the way, go left to right, by the way. If registration record was in the middle, I'm just looking for the, then the X would be in the middle. I'm just looking for the termination. A lot of times, by the way, termination is more like a circle than anything. But anyway, That's how that works. So this guy, what we find out, this is the sequence of events. That's what a sequence diagram is, sequence of events. So, or if you want, you can think of it as sequences of messages. So the student, first thing the student does, requests a fitness class. The manager then checks the schedule, at which point this actor is involved. I don't see that it ever comes back, so I'm not sure what the purpose of checking is, because it might have been a, yeah, go ahead. But anyway, the manager then basically notifies the student. Now, then the student pays, and when the student pays, that's when they're registered, right? So they don't get registered just by trying to do a class. We wait for payment. These kind of diagrams, I would say if you go into a shop and they don't have something like this, there's a lot of knowledge stored in people's heads about when things are supposed to happen. So these kind of diagrams make it pretty crystal clear on how a particular event should take place. So now in your little arsenal of diagrams, I did bring up business process modeling as one set of diagrams. This is another set here that's similar to business process modeling. It's similar. It's just similar enough to screw you up, but it's similar. And then you can decide which is the one that you want to actually employ. Another set of diagrams are state transition diagrams. So before we look at this one, I want you to imagine one of the classic examples is the vending machine. The vending machine, when you show up, is in a certain state, right? And then you throw in some money, maybe. Actually, I tell you what you probably do now is you probably make a selection. As soon as you start making a selection, it enters into another state. Now it's waiting for you to either pay money or for it to time out or whatever. You put money in and enters another state. It delivers your goods and then it returns back to the initial state. So that's how a state diagram is. So in this case, this is talking about the state of an account. So these aren't now objects, even though they have similar looks to them for the diagrams. These are states of an object. So, so the object itself is probably an account. And so when someone opens an account, the account is new. When someone then makes their first deposit, then it becomes active. Now, when they close the account, it's closed, either by the bank or by us, or I guess, I don't know, assets attached. I don't know how that gets frozen, but anyway. But these are just all basically states. They're all states. All right, good deal. And then we're, and so here it's sort of another one with you guys on an ATM, right? You need cash. You put in your card. Now it's in a state. It's looking for a PIN. It's looking for a state. It's looking, you start requesting cash. That's one state. The other one is, by the way, putting cash in, right? But anyway, you request cash. Just as you balance gives you the cash, or that's if the funds are available. If the funds aren't available, then you basically get told no. All right, so there are all those, and then this other diagram, which I've already talked about, is the business process modeling. And actually, I don't know what tool they're using for that, but remember I told you guys about BizAggie. All right. So BizAggie would be a kind of a tool, by the way. You can actually, with BizAggie use a, actually simulate the state. Like, it's not just a glorified PowerPoint. It's a very, very powerful tool. All right, and then the rest of the stuff is just talking about basically, organizing the model and trying to basically, what's this here? Yeah, okay. All right. Of course, by the way, right now is when my daughter has chosen to basically, I don't know what she's doing in the background, but that's quite the distraction. And I'm just going to end the video here. So this is kind of a primer to object-oriented analysis. It's definitely a good deal to review before walking into a shop for an interview, because it shows that you've at least been exposed to some of these ideas, and that'll do you good. All right, so that's it for this one, and we'll see you in the next one.